Hello and welcome to my show called Algorithm Coding with Leaf. It's a title I'm still working on, but we'll work on that eventually. The purpose of this show is to talk about algorithms, coding algorithms, analyzing algorithms, and everything to do with algorithms and programming and the Leaf language. Today, primarily by request, I'm going to cover what's something called time complexity. And time complexity, if you recall, in either my episodes or in other shows, or maybe if you recall from school, I want this big pencil here, you recall something called big O notation, where you have something that's like O of n. It's something like time complexity. If you've been watching my shows, you'll notice that I always say theta and not big O. And we want to understand why am I doing this and what is time complexity. So in this show, what I'm going to do is I'm going to go through the very basics of time complexity, what it is, why do we do it, how do we measure it, and what the purpose of all of this is. If you're unfamiliar with IOM, I'm edA-qa mort-ora-y. I'm a programmer. I do a lot of programming on UI over at Fuse. I'm a creator of the language Leaf. I write a lot of articles, and I'm doing these shows. And if you caught me last night, I'm now learning Rust by playing little coding games online, and it went better than expected. And I'll be doing that again tonight if you're looking for watching. And in this episode, I will go through the basics of time complexity. If you have any questions, feel free to ask. If you didn't catch me live, then just send me a note on Twitter for something you'd like to catch in a further topic. Add a comment over on Twitch or on the eventual YouTube upload. And I'll be covering all of your topics which you request. I just need to know about them. As I said, today is a request about what is time complexity. Actually, the request for me was what is amortized time complexity. But I'm going to take a step back first and talk about just the basic time complexity. We're going to go over this and then figure out what that is. So, without further delay, let's get started on it. I've created some simple algorithms to demonstration. And you'll see it over here. I have an algorithm here. And it's called sum numbers. I'm going to clean up the screen a bit so you see that just in the middle there and get this out of here. So we just have sum numbers. And we're going to try and figure out, well, what does time complexity mean? We know in the general sense it's how long does this algorithm take to run, but it's not a specific run time. It doesn't mean like what's the CPU time. It means how many steps does this take to run. And we're going to qualify steps. So let's go through this, and I'll tell you what the algorithm does first. Sum numbers should be clear. Given an array of floating point numbers, it adds them all up. Now this isn't the cleanest way to code this. You typically wouldn't see this in language, but it helps see exactly where the complexity is. If we look at this, nothing happens on this line. This is just a signature of a function. We don't have anything happening here. We have something happening here. We're assigning a number. And now we have a range of values, so we have to imagine there's an iterator that starts at 0 and goes up through size. So we are doing stuff here. And then we have a total here, and we're adding the number here. And then we return the value. All of these are steps. That is, each of them takes a certain amount of time to do. And so if we said, the biggest ones here is that, let's just put a check mark, we can put little lines beside them. We said, well, this doesn't do anything, this line here. Well, this line does one thing. It's simple. This line also does one thing, and this line does one thing. But what about this line here? What in particular are we doing here? This is a loop. It does several things, but that's not the important bit. The important bit is all of this whole section here. How many times does this happen? Well, this is about this loop here. Whatever this loop is doing it size times. So we have it, we're going to say times size here. We're right times. I'm really bad at writing with a mouse. Sorry about that. Times size. And I'll also use my other hand. My left hand was not drawing there. And so we want to analyze, well, how many times does this happen? We have these 1, 1, 1. We could add them together. And this happens size times. And typically, let me clear this off again. When we talk about time complexity, what we're looking for is a number called t. You notice I'm not saying O. I'm saying t. And there's a difference between t and o. So let's focus on t first. And we have a function t of n. And what does this equal in these cases here? And this is like if we call this function, and we're going to say n is the length of this array. It doesn't always have to be, but for us that's the biggest important thing. So the length of this array, oops, I can backspace that. It's the length of this array, we're going to call it n. And we want to know, given this size of input for this length, how many steps does this program take? And as we said before, this step here takes 1. So we can really say like 1 plus, and then skip over this put here, and there's 1 for the end, we do 1. And then we have a loop which executes size, which is n times. So we have some value x times, oh, it's hard to make little size. Or actually, n. We're going to make it times n. Okay. This is what's known as the time complexity. It's like how long is this loop actually taking? And you notice that when you're used to seeing big O of n, you don't tend to see all these plus ones times x and n. Is you end up seeing something like O of just n. And we can get to it in a further episode exactly how you do this, but I want to focus on this time complexity bit here, how we get this. And this loop should be clear here. We step through n times, and we can actually erase most of the stuff here even as well. Even though we're not talking about complexity, is that when we talk about time complexity, what we're asking is, what operations here are taking lots of time? Like, what is actually costing us something here? And in this case here, we're going to pretend it's this. Whatever this index lookup and this total is, we're going to say this is what costs us all the time. And then in time complexity, we're simply saying, well, then I only care about that operation. How many times does this run? And this runs n times. And that's why my time complexity of n is just n. I mean, okay, I shouldn't have written it there. It is just n. Yeah, okay, sorry, I did. Oh, I might have gone into the thing there. Okay, so this is why we have Tn of n here, is because we're only interested in total equals, and that's how many steps it takes. Given a length of array n, it's going to take n steps to get this population. And now you may wonder, well, why do I ignore this other stuff? And this still has nothing to do with big O notation, so just ignore that and focus on this. And I'm going to clear the screen again. And let me bring a second algorithm into the picture to explain why this is. Because the purpose of analysis is to deal with where is the time actually going. We don't really care about the independent number of steps. We really want to understand, if I'm trying to optimize something, where does all my time actually go? Where is it spent? And so here I said, I'm going to assume this is the expensive operation. On a modern CPU, however, accessing a memory like this in sequence and adding really costs nothing. So that's why I made a second calculation called multiply matrices. And we're going to assume these are matrices. I'm not even going to say the size. This could be a 3 by 3, it could be a 30 by 30, or 40 by 40. Now imagine that when you have a 40 by 40 matrix, you have something like that, and let's just draw this quick matrix here. And we're going to multiply two of them. Can't do dots in this thing. And you have all of these little points in here, all these numbers, and this is just a 3 by 3, and this goes on and on. This is not relevant to the calculation, but when you multiply a matrix, you take each row multiplied by each column. And so a 3 by 3 ends up becoming 9 times these multiplications, 9 times 3, so it's like 27 calculations. And as this goes up n by n, it gets really more expensive. And so what we see in this is that, in this case, this operation is the absolute dominant case. It's overwhelming, the operation here. This other stuff here, who cares? Who cares? It's completely irrelevant based compared to this time. Even the actual iteration variable, the incrementing that takes time. In the case of a multiplication of a matrix, a large matrix, it just really doesn't matter. And so this is why we say the time complexity here is T of n equals n. What we've done is we said that's the dominant operation, and you'll always find this anytime you do time complexity. What you're going to do is you're going to pick out the bits that are really slow, which you think are the problem, and just count them. This is what most people care about, is just counting them. And it's not at all obvious why you do this in all cases, but say we did have an operation like this. If you have this one, clearly, if you have some way to reduce the number of times this is called, you're going to improve the programming. And you can combine this with efficiency profiling. We do profiling on this to help us figure out what those lines are. We don't have to guess. We can run a profile on these programs, and it can point to us saying, look, this code here, it takes a long time. So let's focus on an algorithm that reduces that. And so what I'm saying is, for all of this stuff, we always have these notions of what exactly are we counting, and nobody actually counts all of the operations. If you do look into theory, what you might end up is you might find something called a random. I can't type. It doesn't let me type. Okay. There we go. Do it over here. There's something called a This is getting weird. I can't type in some places. Alright. I'm going to type it somewhere else. Random. Okay, forget it. I'm having bad luck with these programs. Every time I try and draw on the screen, they don't work correctly. Okay, so let's clear the screen again. Uh-oh. I think my program just crashed me drawing. Let's just kill the whole program. Nope. I'll start it up again. So what I have is, I want to say, let me go back to this. When we're talking about individual steps, you'll see in research something called a random access machine. This is one of the machines they use. You don't have to care about it too much, but what it does is it lays out the framework for exactly what you count, what I should and should not be counting here. When you're dealing with practical algorithm analysis, you just never use this. I mean, it's very nice for certain research. When you're dealing with practical analysis, you just don't use this. Just pick out the parts of the algorithm and take long and count how many times they're executed. So let's go down and try another case. I created another one here called print checkered. This prints a checkerboard pattern. And if I comment this out up here again, there's a small error in there that I can't fix right now. We can actually get this to work. Okay, there was a checkerboard pattern there somewhere. Right? So you can see, and I had a bigger test before, and this prints an alternating pattern of checkers. And okay. And we want to know, well, what's the running time of this? So let's ignore that. Let's put that, actually get that out of the way. And we do the same thing here. Well, we have this input. We have rows and columns. And so if we're asking for the time notation, like how long does this actually take, we're going to have a T, and we have columns and rows. That is, given this number of columns and this number of rows, how long does it take? You'll often find in complexity theory, for whatever reason, we love using the letters N and M. That is, it doesn't matter what you've called them here, we use N and M, but I'm choosing R and C here for clarity. And you'll notice in this code now we have two loops. And so this loop is going to execute R times, and the stuff inside this loop is going to execute C times. Now this is basic multiplication. We have something R times C. R, I wish I could do circle here. I wish I could do dots in this program. Apparently I can't. R times C, and the question is times what? What are we doing? What is the dominant operation here? We have this mod operation here. It's an if statement. And the mod says which character to write. I'm going to guess from CPU time that this doesn't take much time, but you might want to count this as 1. But I know from experience that these print statements, they take lots of time. There are items of interest. They're what we actually care about. So we're going to say assign each of them 1. Go back. So they each have a time of 1. Now we don't add them together in this case. We have a conditional branch. Only one of these is executed. You either go here or you go here. So we can count these both as 1, and we're ignoring this cost, so we really just have times 1. So there's not much there at all. So what we have is the time complexity of this is R times C. And this is one of the typical ones, and this belongs to a class of problems that you might find is when we get to complexity later, understand that this is a type of problem you see when people start saying something is n squared. And the reason why it's called that, and again, we're not going to get too detailed into that, is when we start talking about complexity, we're talking about estimates, rough equivalents, and stuff like this. We don't care that these are different values, they're related to each other, so we're just going to call them both n, which means this becomes n by n, it becomes n squared. And I'm doing a lot of hand waving now, and we can get through a detailed analysis of why this does this, but I don't want to get in that now. What I want to focus on is that the time complexity for this is actually R times C times 1. If I had two prints, but we also have the statement down here, 1. If I said this print takes time, then this one here also takes time. So what we also have is that's executed R times as well. For every row, we're printing out a new line. So we actually have this time complexity, R times C times 1 plus R times 1. And that's the complexity for this one. It's a little bit more complex. We calculate it that way. And what we have is, and again, I want to point out, all you're doing is you're counting the statements. This is what time complexity means. Pick what you think is expensive, use a profiler, use your experience, and then just say, how long does this algorithm take? That is, given this input of columns and rows, how many expensive operations does it make? And here we're saying print. And this makes, for rows and columns, R times C times 1 plus R times 1 expensive operations. This is the time complexity of this algorithm. Now both of these cases so far have been fairly simple. And I have another case here where you have to get into another detail of time complexity, is that, well, what if the algorithm doesn't take the same amount of time every time it executes? And let's go down to this index of operation. Get this thing out of the way. Let's just get index of. We have an array and an integer defined. And again, what are we looking for? We want to know, we're going to say the array size, because we have the size over here. Given an array of size n, how many steps does it take? Now, let's start looking at this. Let's look at how the algorithm works. We're looking for this value, find. It's an integer and it's going to be find there. And we just do iterate over it. Now, we said before that this could take n steps, right? I'm going to make a better n than that. N steps. But you'll notice there's a return value in here. As soon as we find it, and as soon as the value we're looking for is the same as the one in the array, we're returning the index of it. And if it's never found, it returns -1. So now let's imagine a series of numbers. And this is where it's going to start getting interesting. And hopefully this text now works. If we have a series of numbers, let's just do something like this. I'll put a few out of order just in case. Alright? And that should be fine. We have these numbers. What if I'm looking for the number 5? If I'm looking for the number 5, let's just write this over here. It stopped writing again, so forget about that. If I'm looking for the number 5 and I have this whole array, well, the length of this array is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we might be saying, look, this equals 13. Oops. Why is this program annoying me so much? Alright, I'm getting really annoyed with these programs. Okay, so we had those three, and now I'm going to write the whole silly numbers again. And let me just write them down again. So whenever I use text, so let's just do 1, 2, 3. Let's just do simple numbers this time. 1, 2, 3, 4, 5. And we had t of n. Wow, I should really get a stylus or tablet. I can actually write better than this. Now say we're looking for the number 3. We want to look for number 3. And so how many steps does it take? Well, this says for each one it steps through, is it the right value? So it's going to step here, here, then here. And on 3 it's going to return. So it takes 3 steps. Now, well, what if we're looking for the value 1? Well, it gets into the loop on the first step. It looks and says, well, no, it only took 1 step. And if we're looking for the value 7, so where's 7? It goes through the algorithm and steps each time. So 1, 2, 3, 4, 5, and then it doesn't find 1. And then it goes to this return 1. And so it's taken not 5, let's say at least 6 steps because it had this extra step, or we can say 5. Now, what's showing here is that, what I want to show is that the time complexity, how long this is taking, depends on the input. And so when we talk about time complexity, we don't ask what is the, we've already said here that it's this comparison that we're of interest, but it depends on this find, not just the array. It depends on the find how many iterations this takes. So what you'll very often find in time complexity is when we're saying this stuff, we don't want to know for an individual case. We're doing something called worst case analysis. That is, assuming this is the worst number we can throw in here, how much time is it going to take? And this is a number that's not found, like 7. So when we throw in 7, we don't find anything. And so you're going to erase all of this. I need a bigger eraser. So if we have an input value of n, and we have, and it's not found, so we're going to assume it's not found, because that's the case where it loops through everything, and the value is not found, we always do n steps. And so that's why we say the time complexity of this algorithm is n. Because we don't care whether we find it or not, what we're saying is the worst case time complexity. And so that's the worst case. I'm going to try typing something again. Worst case. What we also have, it comes up, and sometimes you have it analyzed, is something called average case. Average case. Okay. Now I'm going to explain the difference here. And even though I said we have average case, focus on this here. Most cases, when you do time complexity, you want to know the worst case. There are some cases in time complexity with encryption where you actually want to know the best case. And the best case here for this algorithm is 1. If the item you're looking for happens to be the first one in the array, it takes 1 step. That would be the best case. And other than that, you don't use best case very often. But average case does come up quite a bit. What's the average case of this algorithm? And now we're going to have to start making assumptions. And this is the problem when you start hitting average case. We start making a whole bunch of assumptions. And this average case should be called average input case. Because we have all these numbers here. One could actually argue that the average case, I'm going to put a little wiggly line here instead, wiggly line. If you assume of all the possible integers that can exist, there's an infinite number, very few of them are going to be these values. So in most cases, we're going to step to the end. So the average case, we might want to say it's n. Okay. And this is when I said we have an infinite number of values. So this is when our input is infinite. Now, let's do this when we have a fixed number. So let's say this is a fixed number. And by what this means, like, what if all we ever search for are the numbers 0 to 5? That's all we're looking for. We're going to guarantee that the vast majority of the time, way more than, say, 99% or even 100%, the number will be found. We never hit this condition at the bottom. So we're going to say we never hit here. So that would mean we always find it in here. And the numbers are evenly distributed as well. This is the other one. So we have to have this sort of even distribution of numbers. You can't have like mostly 1. They all have to occur at a certain amount. And then we could say, well, the average time is going to be how many steps does it take? Well, it could take 1 or it could take 6, or 5, sorry. And for our basic math and sequence series, this says n over 2. The average case is going to be half of n. And we do this because sometimes we're interested in the average case. But I actually, one of the people I find it really kind of sketchy. You have to really worry about that. It comes up a lot, though, in programming. There are there's one very big culprit that gets away with using average case, and that's, I'm going to write it nice and big here, a hash map. Okay, and then write this nice and big because whenever you read stuff about complexity, you're going to see hash map, and it's going to refer to stuff like insertion and stuff being O of 1. And I'm going to get into why now, but think about the next time you see something, when somebody says something O of 1, start thinking about it. Well, 1 means there's one operation. That means there's nothing of time complexity 1. That means somebody is really saying that we have a loop that does something that always is constant time. It doesn't matter how big it is. And yes, you should be right to question that, because now you know, well, are we considering worst case or average case? And so these are the two scenarios you consider. Do we have a worst case, or do we have an average case? Or if you're in encryption, do we have the best case scenario? Now let's point on that one, encryption first. The reason why encryption deals with best case scenario is, what if this was a decryption function? Given a public key, how long would it take to find the private keys from it? Now encryption relies on this taking like a huge sum of time, and for the worst case, we don't care about worst case encryption. What we want is the best case. You don't want to choose an encryption algorithm where, for like even the average case takes like, say, 1 billion operations. That doesn't matter, because the purpose is, if 10% of your input only takes 1 operation, like here, then your encryption algorithm is useless, because for 10% of the people it's not going to help them at all. And so that's one of the cases where encryption deals with best case. But again, I will stress, ignore all of this stuff in the bottom. Let's just ignore all this here. Focus on this one up here. If nobody tells you otherwise, and you're just trying to do the typical execution, how long something takes, we look at the worst case. We say, okay, what's the worst that can happen here? There are other scenarios in this. There's also expected case. And this also comes up, and this is one that's very similar to average, but not quite. An average and expected. And the algorithm quicksort is one of the ones that relies on a certain type of input, average case. And you'll often see quicksort quoted with 2 different time complexities for worst case and typical case. Average here is actually the bad word again, right? So this average there is really not a good word. Average, cross that out too, because it never is average. It's not like a statistical average. It's not a mean. It's a typical value or expected value, and so you get in a lot of fuzzy room. So the moment you get down to all this stuff here, it's fuzzy. If you stick to worst case, or actually even best case, it's not fuzzy. It's very clear what those are. And still, I'm talking about time complexities, number of steps. And let me clear all this off again. That was the basics of time complexity. If you have any questions, please ask me now or offline. And that goes through my basic examples. I wanted to go through where this comes from. And again, to focus on that, what we do is, when you want to calculate an algorithm, the time complexity is something called T of n. Oops, that's not the right color. T of n, and that's given an input of size n, how many steps does it take? And we said the sum of numbers. We didn't just count all the steps. We said, let's focus on some steps that are of interest to us. And we said, for example, in this one, we said it's this totaling here. And we used the example from the multiply matrices to convince us that this was the expensive step. And all you do is go through and count them logically, how many times it would take. And if you have a situation where it's a variable number of times, like an index of operation, then what we're talking about is, what's the worst amount of time it can take? We have a second parameter here, What's the worst amount of time it can take given n? And we also said it's n here. We don't consider the shortcutting, and that's the common case. And I think this covers basically what I wanted to do for time complexity. It's a short introduction. I hope it's been helpful for you. If you have any questions about it, please send me a shout on Twitter or comment on the YouTube eventually. Just contact me and I can do another show about specific topics. The next time I do a topic, what I might do is we can either start talking about, well, we've talked about in this show something called big T. It's actually, nobody refers to it as big T. It's just time complexity, T of n. And what you've heard about, though, quite frequently is probably something called O of n, big O notation. And we can say, well, how do you get from this to this? Or, as I quite often mention in my shows, big theta notation. How do I get from that to that? And we also have big sigma. These are the common ones. The most common one is big O, so this one. But, as I said in my other shows, the one you most frequently want is this one. And it's usually, it's usually a problem with the keyboard. And I can cover this in another show then. So please subscribe to my channel so you know about the other show, either in Twitch or on YouTube. And you can also follow me on Twitter because I'll announce it a bit in advance. And if you have a particular topic you're concerned, just again ask me. And after the show on how to do this, I'm going to cover the topic one of my friends requested from me, is that hello M. Rupke. And I'll have another show about what is amortized time. And amortized time is another one that comes up quite often, even if you don't know about it. For example, most of the collections in C++ standard library, and therefore I assume also Java, also Rust, which I'm learning now, and Python, most of them are probably quoted in amortized time as opposed to big O time, or as opposed to worst case complexity. There's all these different times, but they all come down to this. This is the very basic. You have to know how many steps the algorithm is going to take in some theoretical machine. You have everything else is relatively easy to find if you can get this. And this is why we do it, and this is what time complexity basically means. So that's all I have for my show today. Hopefully you will follow me and subscribe to my channels. Later tonight I'm going to be doing another Rust episode where I go on to Coding Game and I solve some of their coding problems. They have the fun little animations with some of them. I don't know Rust, so it's an adventure, so please watch me later tonight, and I'll do that. And next week I'll probably do another Fuse stream, and next Friday is probably going to be my algorithm day. I'll do another Leaf algorithm, and I'll be away from Wednesday next week, so I won't have an episode. So again, the next one will be today at probably a bit later tonight, 10, 11, 12 my time. I'll do the Rust, and next week for algorithms, I can cover one of these ones, or just cover some other random algorithm done in Leaf. Just give me feedback and let me know. And thank you for watching the show. And I hope to see you next time. And get rid of this pointer first. Okay. Thank you.